Hi everybody, welcome to another video in Calculus 1, section 5.3, Fundamental Theorem of Calculus. By the name of it, it is rather important. Right, first, before we actually go to that theorem, we need to define an area function. So let f to be a continuous function for t greater than or equal to a. The area function of f with left endpoint a is given by this. So pretty much we will have the constant a here. That is constant. And the area will count from that on forward. Whenever we have a point x on the right side of a, the area function is defined to be the area, the net area of the function and the x-axis from a to x. So now, it is the net area, just like what we have earlier, but the reason it is a function because the x here is a variable, so we can go from a to that variable, and the variable there have to be different than this variable here when we do the math. So that variable is different than this variable, but what it calculate is the net area between the function, that function, and the x-axis from a to x. Right. So given upon x, we can calculate the area. That's simple enough. That's exactly what this definition is about. So let's look at this example. We define the area function is from -1 to x of f of t dt. This is the graph of f of t. Now first, what is the area function from -1? What is the area function of 3? So if we put 3 in this x, we're going to put 3 on that x on the upper limit. And according to this graph, from -1 to 3, from -1 to 3, the area is equal to 27. However, this is below the x-axis, so the net area is -27. So will be just like that. Next, what is the area from 3 to 3? Now this is the function f of x. Is defined from 3 on. Now we want to evaluate f of 3. F of 3. Yeah, that's why run out of tape. So f of 3 meaning we're going to put 3 on the top. The bottom is still 3. The function. Now we don't even need to look at the graph because this integral, the limits are the same. So from 3 to 3, the width is equal to 0. If the width equal to 0, there's no area. Therefore, it is equal to 0. We don't even need the graph. Right, next. The area function at 9. Meaning we're going to put 9 in to x on the, put 9 to x, which is the upper limit. So from -1 to 9, the 27 is below the x-axis. The 3 is above, so there's a meaning it's plus, and the 35 is below. So we do that. -27, -35 is -62. Plus, this is -59. Yeah, -27 and 3, -24, -59. Yeah. And then if we calculate f of 9, let's do that here. F of 9, meaning we're going to put 9 in for x in that function. So from 3 to 9, there's a 3 on above and a 35 at the bottom. So 3 minus 35, which is negative 32. Right, so it's easy. The area function, we just put the value into it and we replace into the upper limit. The function, area function defined from the constant lower limit, and the variable on the upper limit we just replace by a number, and that's pretty much it. Now let's consider the trapezoid bounded by the line. So now we have the function f of t equal to t plus 3, which is this line, that function. And the area function is defined from the area from 2 to x. The area is from 2 to x. What is a of 2? So a of 2 is easy. Replace 2 in for x. We don't even need the graph. From 2 to 2, the function is defined, and there's no width. Therefore, the area is 0. So that's easy. Next, evaluate the area from 2 to 5, which is a of 5, meaning put 5 in the lower limit. Put 5 in x, which is the upper limit here. Now, if we just want to draw it, it is a trapezoid, right? This is the area. We go from 2 to 5. Because we go from 2 to 5, this is 3. This is the right trapezoid. Next, the function is 2t plus 3. If we put 2 into the function, we have 2 times 2 plus 3, so that will be 7. So this is going to be 7. Right? If we put 2 in here, 2 times 2 is 4 plus 3 is 7. If we put 5 in, 2 times 5 plus 3, that's 13. So we have the area of a trapezoid. 7 and 13 are the bases, 3 is the height. So the area of trapezoid is 1/2 of base 1 plus base 2 times h. So that is the area of the trapezoid. 1/2 times the sum of the bases, 1, 2, times the height is 3. So the area of trapezoid, 1/2, 7 plus 13 times 3. So that is 20, divided by 2 is 10, times 3, that's 30. So the area is 30. Yeah, I'm going to do it using that formula instead of course we can also divide this into a rectangle. And a triangle, which gives us the same thing, which is 30. Now, what if we're going to do that in general for x? Well, in general, if it is just x, we're going to go from 2 to x, f of t dt. So the integral will go from 2 to x, f of t dt. We're going to draw a trapezoid again. Try to find the area of that trapezoid. From 2 to x. The base, the height. By the way, when talking about the height, we should turn it sideways. Bases, the base and the height. So In this case, the height would be x minus 2, which is this is the base. I mean, this is the height. Now a base, when 2 we put in a function, so this is still 7. Yeah, so 1 base. Yeah, when I rather here I'm talking about because the area of that trapezoid. Right, put 2 into the function. 2 times 2 plus 3, so this is 7. This base 7. If we put an x into the function, we will have 2 times x plus 3. Right, so that is the trapezoid. So this area function, we calculate the area of the trapezoid. The area of trapezoid is 1/2 base times 1/2 base 1 plus base 2 times the height. Which is 1/2 base 1, 7, base 2, 2x plus 3 times the height, x minus 2. Right? So base 1 is 7, base 2, 2x plus 3, and times the height, x minus 2. So combine like terms in that bracket, we will have 1/2 7, so it will be 2x plus 10, right? 7 plus 3, and then x minus 2. Now I multiply the 1/2 inside. 1/2 times 2 is 1, 1/2 times 10 is 5, so I have x plus 5 and x minus 2, right? So if we multiply the 1/2, distribute the 1/2 into the first factor, that's what we have. Right, and then we multiply this out. X squared minus 2x plus 5x minus 10. Combine like terms. X squared plus 3x minus 10. So that is the area function. X squared plus 3x minus 10. Right. Finally, the next question is compare the derivative of a to f. So we have the area function is x squared plus 3x minus 10. If we take derivative of the area function, derivative of this is going to be 2x plus 3, right? 2x plus 3. And you say, oh, that is the same as the function, right? Yeah. Even though we write f of t is 2t plus 3. So if we want to replace t by x, we have f of x is equal to 2x plus 3. And the first observation is that they are the same. And that led to the question, is any area function, when we take derivative, is that equal to the function itself? So that question is derivative of the area function the same as the function itself? And the answer is, that is not coincident. It is always the case. And that is the fundamental theorem of calculus. Right. So in this theorem there will be two parts. The first part say that it says if f is continuous function and the area function from a to x and a is positive. When x is bigger than a. So the area from a to some point x on the right side of it. And of course, if the function is continuous and differentiable, the area function satisfies this. So the derivative of the area function is equal to the function itself. So this is, or we write like this. Right. We get back here and we have something a lot more general than this. But for now, the derivative of the area function is the function itself. Right. So that is the first part of fundamental theorem of calculus. However, in the older book, when they mention fundamental theorem of calculus, they mean this one, this part. And this theorem, they say the other fundamental theorem of calculus. So this one is a lot more important than that one. So it says, if f is continuous on the closed interval a to b, and capital F is any antiderivative, then the definite integral from a to b of f of x is equal to the antiderivative, any antiderivative evaluated from a to b. By that I mean we put in b and then we put in a and subtract the result. This is the fundamental theorem of calculus. So what we do is we take the function, go to any antiderivative. Any antiderivative is fine. Evaluate at the limits and subtract them. The shorthand notation is this. Right. The proof is this, just right in picture. The area from a to x plus h is going to be that much. The area from a to x is this much. Now take the big one minus the little one. We have the area, which is the difference between that to subtract that, which is this part here. Next. That area here is estimated by. Now, we take that area, subtract this area, we have this part, right? So this area, this part, this area is estimated by a rectangle. Yeah, which is this rectangle. H is the width and f of x is the height. So we can say the difference of those areas can be estimated as h of f of x. So we write like that. Approximately equal to h of f of x. Of course, this approximation will be better if the h is small. The smaller the interval, the better approximation is. So we divide by h on both sides. Now this is approximation. Now it will become the exact if we have the limit of h go to 0. And of course when we have h go to 0, this exactly is the definition of derivative. So we have derivative of a is equal to f of x. Yeah, so that is the proof of the first part. Of course, the proof of the second part, we can just follow using this picture, but like I said, I'm not gonna do that. But the point here is the fundamental theorem of calculus. This one is more important than the other one. What we do is just find any antiderivative and then put in the limit and subtract. So let's just go to an example here. Let's evaluate that. So when we evaluate this, of course, the first thing realize that we have the limit. So this is definite integral. First we'll find any antiderivative. Any antiderivative will do. So first antiderivative of x and then x squared, right? So we have 60 integral of x. The power rule, increase the power by 1 and divide by the same thing. That is the integral of x. Minus 6 integral of x squared, increase the power by 1, divide by the same thing as the power. And then any antiderivative, if we want all the antiderivative, we're going to have the constant c. I'm just going to put that c here. Later on we can just let c equal to 0. Now, that is all the antiderivative. In the fundamental theorem calculus, we don't need to find any. We can just let c equal to 0. Right. So but that the first step, I just want to do that. Just integrate to evaluate the definite integral. That's how we do. And then we have the limit. So we integrate and then the limit go from 0 to 10. If we want to be absolutely clear, we say x will go from 0 to x equal to 10. Right? Now let's simplify the inside part. 60 divided by 2 is 30x squared. 6 divided by 3 is 2. Plus c. And go from 0 to 10. So 0 to 10. Just like when we find the distance from 2 to x, it is the right point minus the left point, the bigger values minus the lower values, the final minus the initial. So in that case, we're going to put 10 in for x and then put 0 in for x. So 30, 10 squared minus 2, 10 cubed. C is a constant, so I don't do anything with it. So that is where we put in 10 in for x, and then we put in 0 in for x, and we subtract the 2. So that is the fundamental theorem of calculus, right? Find an antiderivative, put in the limits, upper limit, lower limit, and then subtract them. We put in 0, 0, times 0 times 0, so that is just 0. So we have 30 times 10 squared, 100 times 30, 3,000. 10 cubed is 2,000. That is 0 minus plus c. That cancels out, so we have 1,000. And then what we see here is, it doesn't matter what the constant is, the the constant cancel itself. So later on, we just choose c to be 0. So we don't have to worry about that constant. Or that constant could be anything, but we choose to be 0 for convenience. So we choose the constant to be 0, so we don't have to worry about that. To simplify the verse. So, of course, that is a definite integral. Our calculator can do definite integral. Math. Option number 9. Go in from 0 to 10 of 60x minus 6x squared dx. That is 1,000, right? Now, I just want to show this one time. If your calculator is in the older model, like TI-83 or the early edition of TI-84, we have in the classic view, when we hit math number 9, math number 9, this is what we see, finite integral, which is perfect, which is perfectly fine. We will still enter 60x minus 6x squared. This is a function. The variable is x. That goes from 0 to 10. And that gives us the same thing. So the syntax here is finite integral. We enter the function, indicate the variable, and then lower limit, comma, upper limit. That will work. Right. Now let's look at the next example. Find the integral from 0 to 2 pi of 3 sine x minus 2. So we'll do one by one. Integral of sine x. Integral of sine is negative cosine there's a 3 in front of it, and integral of a constant 2. Integral of constant, we just multiply x to it, and we go from 0 to 2 pi. Right. Then we just put 2 pi in let's just rewrite this first. Negative 3 cosine of x minus 2x. Yeah, if it's clear, we just say go from 2 pi without no writing x, go from 0 to x to equal to 2 pi, because x is the only variable here, so we just need to write like that. And of course there's no constant c because we let c equal to 0. Yeah. So later on, for a definite integral, we don't need to write a constant c, just need to evaluate the limit. Right, put in 2 pi, negative 3 cosine of 2 pi minus 2 times 2 pi minus negative 3 cosine of 0 minus 2 times 0. Yeah, just put in the upper limit first, put in the lower limit, and then subtract the result. Cosine of 2 pi is the same as cosine of 0, which is 1. So we have negative 3 times 1, or negative 3, minus 4 pi. Cosine of 0 is 1, minus negative 3 times 1 is plus 3, and then minus, and that's just plus 0. So we have negative 4 pi. So if we want to check our answer, make sure it is in the radian mode when we do this. Math number 9, the function is 3 sine x minus 2. The variable, let's close that. The variable is x. That goes from 0 to 2 pi. Wait, sorry, I put the parentheses at the wrong place. That's what I mean, sorry. Now, and we have negative 4 pi. So of course the same thing. However, like I said, for this kind of problem on the test or in the homework, sometimes we have to do it by hand because the calculator only give us the decimal number. My math lab sometimes do not take decimal number as the answer. They want the exact number. In that case, we have to enter negative 4 pi. The only way we can get the answer, exact answer, is to do it by hand. So that's what we have. Right. Now, this is one way to do that. one way to do the problem. The other way to do the problem is can always do this. Can always split the function from 0 to 2 pi 3 sine x dx, and then minus integral from 0 to 2 pi 2 dx, and then we do each one of them separately because we did this before. So that 3 cosine of x go from 0 to 2 pi, and then 2x go from 0 to 2 pi. Yeah, you can just split them, do separately. Put in 2 pi, then put in 0, put in 2 pi, and then put in 0. Just make sure that it is minus, so that will be a plus. Be careful when we do this. I recommend that we do not write like that when we have the integral that has the minus like this. Just put the parentheses here, and the upper limit minus the lower limit. Just put the parentheses there. This case it doesn't matter because it is 0. Yeah, so we can just split the integral into individual one, and then we just put in the numbers and then evaluate. Same thing, right? So the nice thing, I recommend that even though you don't use a calculator to get the answer, but we can use a calculator to somehow check the answer, even though the calculator did not give us for negative 4 pi, but at least the values are the same. So that is some kind of, somehow we check the answer. That I recommend that you do for any definite integral. Right, next, do this one. So, in order to do this, we need to rewrite because if it is not a trig function, we use the power rule, and so we have to write that as a power x squared at the bottom, meaning x to negative 2, and square root of x, meaning x to the 1/2. Now we integrate. Power rule. X to negative 2. Increase the power by 1. Negative 2 plus 1 is negative 1. Divide by the same thing as a power. So that is the integral of x to negative 2. Minus 3. X to the 1/2 integral. The power rule is increase the power by 1, 1/2 plus 1, 3/2 over 3/2. And then the constant c will let equal to 0. So we will evaluate this from 1 to 3. Right. Now, divide by negative 1 is going to be negative, so the first one is not going to be much. Right. Next, to simplify the numbers here, remember from section 4.9, if we have 3/2 at the bottom, that means we multiply reciprocal. And then we have x to the 3/2, going from 1 to 3. Right. Now, x to negative 1, we can flip it, become 1 over x. And then the 3 and the 3 cancel, 2 x to the 3/2. Now I'm going from 1 to 3. We're going to put 3 in for x. And then we will put 1 in for x. Right, simplify this and we have 1/3, 2 times 3 to the 3 half minus 1 over 1 is minus 1 minus a negative, that's a plus. 1 to the 3 half is still 1, so we just have plus 2. Right. So we can pretty much do everything except for 3 to the 3 half. We're just going to leave it like that. So 1/3 minus 1 plus 2. So let's simplify that. 1/3 minus 1 plus 2. Right. Change that to fraction of 4 over 3. By the way, I should change this back to the nicer displays. Yeah, they give us 4 over 3. And then we still have this. Right, 2 times 3 to the 3 half. Yeah, so that is the answer. If we want to write this, it's the better way, then we can write this 3 to the 3 half. So what is that? So 3 to the 3 half is 3 to the first and then 3 to the 1 half, right? We can split as the whole number. Right? 1 plus 1 half is 3 half. So we split the whole part and then the decimal, the fractional part. And then we have 4/3. 3 to the first power is 6. And 3 to the 1 half, we can say square root of 3. Yeah, so this is the nicest answer that we have. So let's just do that and see what is the values. 4/3 minus 6 times square root of 3. Right, so that's what we have. Now, if we do this by hand, if we use the calculator, let's go from 1 to 3. 1 over x squared minus 3 square root of x dx. So the calculator gives us that. So obviously either I did something wrong or the calculator did something wrong. So let's go back to check the worth. So that's why we check, right? Right, so that 1 half, 3 half, 3 half, 2/3, 3 cancel 2, 3 half, 2. Equal 1 to 3, 1 over x squared minus 3 squared over x. Alright, I see where it is. So that's why we check, right? Yeah. Divide by -1, I forgot that. So this will be negative. So negative. So that will be a plus. Yeah, other than that, let's see. 1 and 1 plus 2 minus 1/3. So that is a over 3 instead. Yeah. So that's why we check the answer, right? So it's 8 over 3 instead. So once again, this is the calculator answer, and our answer are the same. So yeah, so don't make the same mistake that I did here, which is forgot the negative. Right. So this 8 over 3 minus 6 square root of 3. This just show that I do the problem live. I did not do anything before recording. Right. Now, next, use the graph there. Find the net area of the region bounded by the curve from -1 to 2. So pretty much we just need to do this. -1 to 2. The function dx. Yeah, that exactly will give us the net area from -2, our -1 to 2, the function. Right. So we have this. I will multiply this out first because we're going to use the product rule. I'm sorry, there's no product rule. We use the power rule. So I just multiply it out and put it in here. So that gives us, I keep the 6x, x squared minus 2x plus x minus 2. Right. Just one more thing I forgot to say it on the last problem. 3 this answer, we get the answer by hand. The calculator can only give us the decimal answer, but the calculator can help us check to see if actually our answer is good or not. I mean, it is close. If there is some decimal rounding off, that's still fine because the calculator does have some error, but the calculator will not give us the answer like this in this form. Yeah, so we have to get the answer this by hand. If your calculator can give you this answer, you cannot use that calculator on the test. Right. Anyway, so yeah, that's the only reason this calculator is allowed on the test. Because if your calculator can give you the 8 over 3 minus 6 times square root of 3, what is the point of learning all of this? Minus x minus 2. Right? And then multiply it out. 6x cubed minus 6x squared minus 12x. Right. X squared minus x minus 2. 6x cubed minus 6x squared minus 12x. Alright, so we'll evaluate that. Right. Now we just integrate 6x cubed integral of x, increase the power by 1, divide by the same as the power. X squared x cubed over 3 12 integral of x squared over 2. Yeah, just like derivative, just like limit, summation. When we do that for the one big function, we can always break it down into individual terms. And by terms, I mean the terms are connected by plus or minus. If it is multiply, we cannot do that. There's no product rule in integral. So that's why I multiplied it out first. Right? And of course, let the constant c be 0 in this case, going from -1 to 2. Right. And then simplify. Of course, you can just take 6 divided by 4, but if you're not sure about what to do, there's always self. We say that if we have a number at the bottom, we're going to flip that. Then we can flip it. Going from -1 to 2. Right, 6 times 1/4 is 3/2. X to the 4th minus 2 x cubed minus 6 x squared going from -1 to 2. So put in the upper limit. And then the lower limit. So that is where we put in the upper limit. And we subtract. Put in the lower limit. Right. Now, since this is a function, put in the limit, I can just do this. First, I'm putting 2 in the function, right? So 2 is turned to x. And I will enter this. 3 over 2. 3 over 2, I can just type 1.5. Sometimes little things like this will self. Sometimes. 2x cubed, you can type x. But I just type x cubed here. Minus 6x squared. So when x equal to 2, this is equal to -16. Yeah, to evaluate all that. Minus, when we put in -1, it's turned to x. Evaluate this function. -2.5. And then finally we have that. Subtract that. Or we should do by hand now. Just make sure that is correct. I would check. By using the calculator. That go from -1 to 2. Let's see if we can do this. Sorry, that's not what I meant. Let's try again. Math number 9. That go from -1 to 2. I try to paste the function here. Yep. And that would be wrong. Because yeah, this is the function. This is the antiderivative. We're not using the antiderivative here. Sorry. Don't put that antiderivative. because the function is 6x cubed. It's better yet just enter from the beginning. 6x, x plus 1, x minus 2 dx. Yeah, so that should be the same. So that gives us the net area be this much. Simple enough, right? Yeah, so just integrate, get an antiderivative. Usually we just let c equal to 0, put in the upper limit, put in the lower limit, and subtract. So that is very fundamental. Of course, fundamental to calculus, right? Now, so this is find the net area. The net area is equal to the definite integral. Whereas this is just the area, which is different. Notice that if we want the total area here, R1 should be positive, R2 should be positive, and we add both of them up, that should be positive. The area, what we have here, is going to be positive. So, in this case, if we want to find the area here must be positive. Of course, it could be 0, so I just say area must be greater than or equal to 0. So in this case, we have to do the area R1 first. The area R1 is the integral that goes from -1 to 0 based on the graph. And we have the function. Now, let's say we sort of have the calculator and we don't want to, of course, I can just evaluate this, change the limit. That's easy, right? But if we want to at least put some work on it, we did integrate f of x, right? Which is this function here. So the antiderivative is still the same, right? We just change the limit, we don't change the function. So therefore we still have the same thing here. So I would just say this is equal to 3/2 x to the 4th minus 2x cubed minus 6x squared. I need to pause the video for 1 second. Right, we continue. Sorry about that. So we have the same antiderivative, the same integral. Now just need to put in the limit, but this time it is from -1 to 2, not from -1 to 0. Sorry, -1 to 0. That's what we have here. Now, since we have the function, we entered that in the calculator already. Now I'm just going to put x star to 0, which we cannot do that. I mean 0 star to x. And then the function, alright, which is this, is the integral. We do that because we have 0. Because so put in 0, that's what we have. And then put in -1. We should have -2.5, which we already did, but I'll do that again. So when we found the integral, just put in the limit. At 2.5. So that is R1. R2 is from 1 to 2. I mean, sorry, 0 to 2. Right. However, if we do that, it is going to be negative. If we guarantee that the area must be greater than or equal to 0, since R2 is below the x-axis, we have to throw in an extra negative to guarantee that the area is going to be positive. Right. But the integral is still the same. definite integral, I mean still the same integral, the same antiderivative. This time go from 0 to 2. I throw an extra negative to it because it is below the x-axis. Right. Put in 2, what do we have? It should be negative 16, but once again I do that. And we will have negative 16. And then put in 0, we have 0. And then so this is positive 16. Of course, the error must be positive. We have this negative here once again because it is below the x-axis. So we have to put the extra negative sign if the region is below the x-axis. If we want the area and that region is below the x-axis, we have to throw in an extra negative. And then when we want the total area, we just add them up. That is 18.5. So that is the total area. So be careful if the question asks for the area or the net area. Net area or definite integral is still the same. But if it asks for the area, we have to split, do whatever area above, and then find the definite for the one below. Put an extra negative to guarantee that the area is positive, to guarantee that we have a positive number for the area. Of course, we still can get 0, but anyway, add them up. That is the total area. So that is the difference between the area and the net area. Right. Yeah. Of course, you can do that by hand, or once you get to an antiderivative, you can just evaluate the endpoint using the calculator, like what I do here. Right. So that is the second part of the fundamental theory of calculus, or we should just say that is the fundamental theory of calculus, because later on when you go to Cal 2, Cal 3, every time we refer to fundamental theory of calculus, we will refer to this one. Now go to the other fundamental theorem of calculus, which means, which is the derivative of the area function is equal to the function itself. However, I'm going to write this in the more advanced formula, which will help us a lot more. So remember, we have the note, we didn't have anything there. Now, I write this theorem, it is called the Left Theorem. You don't even need to know the name, but so we have the derivative with respect to x of an integral. Now if we have both lower and upper limit, the lower limit, let's say we have g of x, the upper limit is h of x. So we will take the derivative of the integral lower limit g of x, upper limit f of x, which is the function of x. In there we just have the function of t dt. So derivative of the integral. Now this first we're going to, of course we don't do the antiderivative because later on we do the derivative. Remember, derivative and antiderivative somehow they cancel out, because we have the function, we have the function. If we take derivative, we have this derivative. Antiderivative, we have that plus c. Right, so they somehow they're the same. So in that case, we don't do any integral here. According to that theorem, it's just equal to a function. But this time we have the limit are more complicated than just a and x. So in general, what we do is we're going to put h of x into here, and then we have to multiply by the derivative of it with respect to x. So upper limit, and now we put in the lower limit. The chain rule in effect, we multiply by the derivative of the limit itself. So this is the Leibniz theorem. Right. I might misspell it. Let's see. I think that. Let me pause the video and look it up to see if it is correct. It is correct, yes, it's spelled like that. So that is that Leibniz theorem. So the other part of the fundamental theorem calculus is if we have the derivative of the integral where we have the limits as function, put in the upper limit, multiply by the derivative of it, subtract, put in the lower limit, multiply by the derivative of it. So that's simple enough, right? Right, so here we have the derivative of the integral. So what we do is first, the function is still the same. But we put in the upper limit in for the variable t, and then we have the derivative of the upper limit. Subtract, the function is still the same. Now put in the lower limit, and then derivative of that lower limit. Derivative of x is just 1. Derivative of constant is 0. Bottom line, we just have sine square. So that's what we have. Right? Pretty simple. We don't have to do any integral here. Just substitute in the limit, multiply by the derivative of the limit for the upper limit, and then subtract, same thing for the lower limit. Right? So that is the Leibniz theorem. Same thing here. The function is still the same, but instead of t, I'm going to replace by the upper limit, and then times the derivative of that limit. Then subtract, same thing, but instead of t, replace by the limit. This time is x, and then we multiply by the derivative of it. Simple enough, right? Notice that derivative of x is going to be 1. Derivative of a constant is equal to 0, so we don't have anything there. So the answer is just negative square root of x squared plus 1. Simple enough, right? And it's just pretty much just that. Next, now we have both the limits are function, right? So first, replace the variable by the limit. The variable is t. When we have t dt here, so the variable is t. Replace that with the limit, and then multiply by the derivative of the limit. Subtract the function. Now put in the lower limit, and then derivative of the limit. It's always like that. So I have cosine of 3x squared. 3x squared, that gives us 6x. Cosine of x squared, derivative of x squared is 2x. Right, I can move the 6x in front. And then the 2x in front. Right, notice that we cannot combine these two because this cosine of 3x squared, cosine of x squared, cannot combine them. So that's as far as we go. So that is the other fundamental theorem of calculus. Substitute the limit into the function. Don't do any antiderivative here because we have the derivative. The difference is there's the derivative. And the way it looks, we have derivative with respect to x. That will have to be the same as the variable of the limits. The inside of the integral, different variable. Any variable, they have to be different than this. So the limits and d over dx and the derivative have to be the same variable. The integrand, the function, and d, whatever it is, have to be the same variable. We can write u, v, or whatever it is. This variable will be the same. This variable will be the same. Right. Now, so that's pretty much what we have for this section. Just do one more example for each one of them. Evaluate this. So first, don't have the limit, don't have the derivative here. So this is just the fundamental theorem of calculus. We integrate. Integral cosine is sine. And there's a 2 in front of it. Evaluate from pi over 3 to pi over 2. Right. Put in the upper limit. Subtract. Put in the lower limit. Alright. And sine pi over 2 is sine of 90 degrees, which is 1. And sine of pi over 3 or sine of 60 degrees is square of 3 over 2. Cancel out the 2 here. We have 2 minus square root of 3. Right. Of course, we still can check the answer. The calculator will not give us this answer, but at least somehow we can get something similar, something close to each other. From pi over 3 to pi over 2. 2 cosine x dx. We have that. So how about 2 minus square root of 3? Yeah, so we good. Oh, by the way, make sure that it is in the radian mode when we do this. If there's a trig function. Right. Which it is. Right. Next, this is the other fundamental theorem of calculus because we have the derivative. So if that is the case, by the way, when we see this, it will be a lot more convenient. If I'm just move the dt on the back, I just want to have the function in the middle. And the dt or dx, whatever it is, at the back, like this. So we write like this. It is easier to see what the function we're dealing with. And then, the other fundamental theorem of calculus, replace the variable here with the limit. And then times the derivative of that limit. Same thing for the lower limit. Replace the variable with the lower limit. Times derivative of the limit itself. Yeah, so derivative of sine x is cosine x. Derivative of constant is 0. Yeah. So that is 0, and we have negative 1 over sine x squared we can write as like that, plus 1 times cosine of x. We can just multiply cosine of x on the top, and that gives us negative cosine of x sine squared plus 1. Right. So these together, those are the fundamental theorem of calculus. As always, thank you for watching. See you in another video in Calculus 1.